Yes, sir.
I said this very last thing. Okay, that's got to do with how atomic mass is calculated. Okay, specifically, we're going to talk about relative atomic mass, and we're also going to talk about the relative isotopic mass. So there are two different things. Now, the first thing is the definition of what relative atomic mass is. It is the average mass of an atom of an element so it's the average mass of an atom of an element compared to 1/12 the mass of a carbon-12 isotope. So compared to 1/12 the mass of a carbon of a carbon-12 isotope. I said now, so that is the relative atomic mass. The reason it's the average mass is that different atoms have different isotopes. So different atoms, they have different isotopes. And for example, you've got chlorine, which is 35, and chlorine, which is 37. So when we take the average, it comes out to be equal to, the average value comes out to be equal to around 35.5.
So are we studying moles today?
Yes, that's the last thing. Okay, then we're going to start with the other chapters. Okay, we'll do the calculation chapters first. Specifically, we'll do energetics after this. Okay.
So we're done with redox.
Yes, redox reaction. हम redox कह रहे थे.
हाँ नहीं उसके moles के we'll do some more moles questions. ठीक है. It's basically the same question except for that balancing thing. ठीक है. So we were done with balancing. All you have to do is the question is kind of the same. It's the same moles question. There's nothing different to it, except for the fact. Where's the worksheet? Just a second. Here's a worksheet. So we'll practice some more questions. Just a second. Like redox and titration, right? So it's kind of the same question, except that that you just have to balance this equation. That's it. I mean, that's the only additional thing that you have to know about. Okay, so probably the next class tomorrow we'll probably do some more practice of these. Okay.
Okay.
So now, and this is still part of moles. We're going to do some more practice of these questions. Now, I was talking about relative atomic mass. It's the average mass of an atom of an element. Why is it an average? Because different atoms, sorry, not different atoms, the same element. So the same element or atoms have different isotopes, or not atoms actually. Elements have different isotopes. When we talk about the chlorine as an element, they're going to have different isotopes. So there's chlorine 37, there's chlorine 35, and the average comes out to be around 35.5. So that is why it's the average mass of an atom, because you've got different isotopes. Now, the other thing which I think I did tell you earlier as well is, remember the difference between nuclear number and the mass number. So when you talk about the nuclear number, so when you talk about the nuclear number is a count. It's the number of protons plus the number of neutrons. And it's always going to be a whole number. A nuclear number is always, when you're counting things, okay? So if somebody tells you like there's a plate that's full of apples and they tell you how many apples you've got, it's always going to be a whole number. It's going to be either 4 apples or 5 apples or 2 apples. So it's always going to be a whole number. Okay? So remember that. A nuclear number is always a whole number. And never write decimals with it. So if chlorine is 35, then it's exactly 35, not 35.0. Because the moment you introduce a decimal, you're suggesting that it could be 35.1 or 35.01 or something like that. So remember, when you're counting things, countable things are always whole numbers. It's either 1 or 2 or 3 or 4. So the nuclear number is always a whole number. And the nuclear number is very similar to the mass number. But I had previously told you that they kind of represent the same thing. But when you measure the mass is never going to be a whole number. For example, if somebody tells you what is the mass of those apples, the mass depends on the accuracy of your device. For example, those apples could weigh 5 kg, or they could weigh, if the device is more accurate, it could weigh 5.1 kg. If it's even more accurate, it could weigh 5.167 kg. So the atomic mass is always going to come. I mean, it can come in decimals. It's always written in decimals, and depends. And it depends on the accuracy of the device. So I've got chlorine 35. It's got a nuclear number of 35. That's a whole number. What that basically indicates is that when you have chlorine 35, you've got 17 protons and you've got 18 neutrons. So that's a whole number. Both of these values are going to be whole numbers. But if you look at the mass of the chlorine 35 isotope, so for example, if I just Google it, chlorine 35 isotope, and if I look at the mass, now you can see that the mass is not coming out to be exactly 35. The reason it's coming out to be very close to 35 is that protons and neutrons have a relative mass of approximately 1, but it's not exactly 1. So the mass of this chlorine 35 is coming out to be what? It's coming out to be 34. I mean, it depends on the accuracy of the device. So it comes out to be this value, which I've posted over here. That's the mass value. That's the mass of this, or the relative mass. The reason we talk about the relative mass is because we're comparing everything to. So we are comparing everything to carbon 12. So is this point clear? That protons and neutrons have an approximate mass of 1, but not exactly 1. Like the accurate mass, I mean, I'll just Google this, the accurate relative mass of a proton. So it's not exactly 1. I mean, you've always studied in O levels that the mass of a proton is 1. But now you've realized that mass depends on accuracy. Whenever you talk about weighing something or measuring the mass of a substance, it depends on the device. How accurate is the device? So this one is coming out to, so you can see that it's clearly not equal to, it's not exactly equal to 1. The accurate mass of a neutron would be slightly different, I think. So the relative mass of a neutron, it's not probably I mean, I'm not getting that over here, but you pretty much get the idea. Just a second. If there's no, it's not anywhere. So here's the mass of a proton, the resulting relative mass of a proton. So the point is, coming back to the point, nuclear numbers are always a whole number. They're always going to come out to be a whole number. But when you talk about the mass value would be kind of exactly the same, but not a whole number. It's going to be in decimals, and it will come out to be something close to the nuclear number, because the relative mass of a proton is approximately 1, but not exactly 1. So is this point clear? What's the difference between a nuclear number and what's the difference between the atomic mass? You clear, yes or no?
Yes, sir.
Yes.
Now the next thing is, how do you calculate the average mass of an ice? Yes.
Sir, isn't it 35.5?
क्या नहीं ये मैं नहीं वो तो दोनों क्लोरीन्स का मिला के it's 35.5. ठीक है. तो मैं इधर isotopic mass भी लिख देता हूँ. What is isotopic mass? Isotopic mass is the average mass of, but it's the same definition. So I'll just write the definition of what an isotopic mass is. तो याद रखो अभी हम isotope की mass कर रहे थे. So it's the average mass of an isotope of one single isotope of an element compared to 1/12 the mass of a carbon as a compare carbon-12 atom. So everything is being the relative mass, everything is being compared to, it's being compared to carbon-12. So just remember this, when you see chlorine-35, that's the nuclear number. The actual mass is not actually 35, it's something close to 35, but not exactly 35. And always remember, the mass is always going to be in decimals. The nuclear number is always going to be a whole number, because that's where you're counting things. This is where you're measuring things. Okay. So now moving on from this, what are we supposed to do this? The first thing is we're going to do some little background of mass spectroscopy. Okay, remember, most of mass spectroscopy is in A2. Now,
Sir,
yes.
could you just scroll up a bit? I just wanted to write the last line of isotopic mass.
Okay.
Yeah, thank you.
So mass spectroscopy. The reason we're going to study mass spectroscopy is, how do you measure the mass of an atom? Like the atom is really tiny. So it's kind of, you don't have devices that can actually, like, you don't have a weighing balance where you can put the atom and you can measure the mass. What they do is, there's a thing called mass spectroscopy. At the moment, you should just know the general idea of what mass spectroscopy is. The details are in A2. So no one is going to ask you any details about mass spectroscopy, but you're going to get questions on mass spectroscopy. In the questions, they're going to use the term mass spectroscopy. So directly, they're not going to ask you anything about this. So for example, I've got a chlorine atom, and I want to measure the mass of a chlorine atom. What I do is I ionize it, which means that I turn it into Cl plus 1 ion. Then I've got these chlorine ions. What I do next is I turn those chlorine ions into a beam of particles. So you've got lots of Cl plus 1 ions traveling. All sorts of Cl plus 1 ions. They're moving around in that beam. Now we just discussed that chlorine has 2 isotopes, and both of them have different masses. You got an isotope which has a nuclear number of 35. You've got an isotope which has a nuclear number of 37. So you've got these 2 different ions. weighing some, I mean the masses are slightly different. Now what you do is, there's a beam of charged particles and you pass it through a magnetic field. So here's a magnetic field, and if you know some basic physics, you would know that charged particles, they kind of tend to deflect in a magnetic field. So your beam of charged particles, hopefully everyone knows that, like current is a beam, it's basically charged particles, and current, a wire that's carrying current. You know the left hand and the right hand rules. I think it's the left hand rule. So whenever you have a charged particle and they're flowing through a magnetic field, they get deflected. So the beam of charged particles is going to get deflected. And so it's going to get deflected in the magnetic field. So that's one deflection. There's going to be another deflection. So the beam actually splits up into two parts. So we need to first discuss what does deflection depend on? Deflection depends on two things. It's directly proportional to the charge of the particles, and it's inversely proportional to the mass of the particles. Now, from this relationship, what you can figure out is that the mass and the deflection are inversely proportional. Like if the particles are heavy, they're going to deflect less. If the particles are light, they're going to deflect more. So the deflection kind of like you've got detectors over here. You're detecting where are those charged particles? Where are you detecting those charged particles? So what you do is you don't have a weighing balance. What you do is you look at the deflection and you convert it. You've calibrated this. So you look at the deflection and you convert it into mass, because a heavy particle is going to be deflected less. A light particle will be deflected more. For example, this chlorine 37 is a heavy particle. So you're going to get chlorine 37 over here. It's a heavy particle. It's going to be deflected less. And the chlorine 35 is a lighter particle. So it's going to be deflected. It's going to be deflected more. So is this point clear so far? What does mass spectroscopy do? Yes or no? Is okay. Hania, is this clear? Mahat, Ahmed?
Yes, sir.
Achha. Now just remember that you can have all sorts of particles. I mean, that's how you measure the mass of all the particles. I mean, if you have hydrogen atom, hydrogen has a mass of 1, so it's going to be deflected a lot. So you'll just keep on looking at the deflections. If the angle of the deflection is large, that means the particle is really light, and if the deflection is less, the particle is really heavy. So this is where you get the relative atomic masses or the relative isotopic masses of different atoms or their isotopes. Okay, that's how you measure the mass of an atom, by looking at the deflection. Okay, you just change it and you compare it to the carbon-12 deflection. Like if something is deflecting twice as much as carbon-12, that means it's twice as light. If something is deflecting less than carbon-12, then that means it's heavier than carbon-12. So anyways, you can basically measure the mass. So I've got a detector over here. Now the good thing about mass spectroscopy is it not only gives you an idea about the mass. So here's my detector at this. कौन सा?
So can you please repeat the carbon वाली चीज अभी जो आपने बताया?
कि वो carbon-12 वाली?
जी सर कि उससे अगर heavy हो.
नहीं, वही है ना कि एक particle है that's carbon-12, ठीक है? हम सारों को carbon-12, we comparing it with carbon-12, ठीक है? But बहुत पहले ना carbon-12 was chosen as a standard because carbon was everywhere, ठीक है? So because of its abundance. Now carbon-12 और एक मेरे पास था magnesium है, which is 24. मुझे बताओ, how did you figure out that magnesium is twice as heavy? आपने क्या चीज देखी थी? How did you figure out that magnesium is twice as heavy as carbon-12? You figured out? नहीं, उसकी deflection आपने देखी थी कि जब आप इसको आयनाइज
हाँ,
करोगे
ठीक।
दोनों को, if you get charged particles, ठीक है, remember the charge is always +1. I mean, you ionize it in such a way that the charge is constant.
Okay, sir.
ठीक है, so it's obvious that this deflection would be half क्योंकि it's heavy. तो इसकी डिफ्लेक्शन कम होगी और इसकी डिफ्लेक्शन ज्यादा होगी, उससे आपने आइडिया लगा लिया कि भाई ये हैवी होगा उससे, ठीक है। अच्छा, सिमिलरली इफ यू हैव 6 वाला कौन सा होता है, व्हाट इज 6 विद द मास ऑफ 6? आई डोंट थिंक देयर इज एनीवन विद मास ऑफ 6, लेकिन but anyways, that's how you figure out कि हाँ क्या चीज?
तो क्लोरीन और कार्बन को कंपेयर करेंगे, क्लोरीन और कार्बन को, तो फिर उसका कैसे पता चलेगा कि वो तो हमें समझ आ रहा है कि वो डिफ्लेक्ट ज्यादा ही करेगा क्योंकि वो क्लोरीन से ज्यादा ही हैवी है।
नहीं, हाँ, कार्बन ज्यादा डिफ्लेक्ट करेगा ना, लाइक इफ अगर इस बीम में इस बीम में कार्बन भी होता है 12+ और उसका चार्ज प्लस होता है, ठीक है, सो कार्बन वाज लाइटर, सो उसकी डिफ्लेक्शन ज्यादा होती ना।
एग्जैक्ट तो नहीं पता होना चाहिए ना, मतलब हमें बस ये पता होना चाहिए कि वो ज्यादा डिफ्लेक्ट करेगा।
हाँ, बस और थोड़ा सा ये आइडिया होना चाहिए कि दिस इज हाउ यू मेजर द मास ऑफ द पार्टिकल्स, कि यू लुक एट द डिफ्लेक्शन एंड यू कन्वर्ट दैट इनटू मास। आपने कैलिब्रेट किया हुआ है, डिफ्लेक्शन ज्यादा होगी तो मास कम होगी, डिफ्लेक्शन कम होगी तो मास ज्यादा होगी, ठीक है, क्लियर है ये?
यस सर।
अच्छा, लेकिन I was coming to the point कि let's just focus on chlorine. Now, chlorine has 2 isotopes and both of them have different masses. One of them, the lighter one, is deflecting more, the heavier one is deflecting less. By looking at the deflection, you were able to figure out that one of them had a relative mass of 35, and the other one had a relative mass of 37. So, ab isme na you get another thing as well. There's a y-axis as well. Not only do you get the mass, so this is referred to as m over e, which is basically mass. I mean, mass over charge. I mean, the charge is constant. You always turn it into a +1 ion, so the charge is constant. Remember, even if they don't form positive charges, you're doing this in the lab. You forcefully turn them into +1 ions. So whenever you do mass spectroscopy, you always do it for a +1, whether it's carbon, whether it's chlorine, whether it's any other element. आप जब उसको ionize करते हो, you always turn it into a +1. So you want to keep the charge constant. अच्छा, so इसको m over e axis कहते हैं, which is basically mass. I mean, this is basically mass. अच्छा, so not only do you detect that there are 2 different masses, chlorine atom has 2 different masses. One is heavy, one is light. So that means it has 2 different isotopes. But you detect another thing, and that's the y-axis. So what is at the y-axis? You detect the relative abundance. The relative abundance. ठीक है, what you detect is कि भाई आपको how many, यानी if you have a chlorine atom, so how many Cl +1, हाँ, तो आपके पास बीम के अंदर ना कितने Cl37 आ रहे हैं, and how many Cl35 are you getting? Detector is detecting that as well. So for every Cl37 that's detected, दूसरी साइड पे ना there are 3 Cl35s that are coming in, which basically means that in the chlorine sample, you have a lot more of chlorine 35 and a lot less of chlorine 37. So what you detect is the relative abundance, which is कि आपको पता लग जाए chlorine 35, you're detecting more of them, and the chlorine 37, you're detecting less of them. Now, this detection could be translated in terms of percentage. For example, you might have a percentage of 75% or 3:1. What that basically means is that for every 3 chlorine 35s getting detected, you're getting just one chlorine 37. So when आपके पास beam of particles था, you had a sample of chlorine and you did mass spectroscopy. The ions passed through the magnetic field, they got deflected. Heavy ones, come deflection, light ones, other deflection. But you were getting a lot of these light ones and very few of the heavy ones. So you were able to figure out the relative abundance as well, that you're getting more of 35 and you're getting less of 37. So is this clear as well?
Yes, sir.
Okay, everyone else, is this clear? Ahmed, Anya, Wafa, Amna, is this clear?
Yes, sir.
Achha, so what do you do with this?
Sir,
Yes.
I don't understand the 3 and 1 bit.
No, it's just that I mean, this one has already been calculated. What that means is, remember you took a sample of chlorine, right? And the chlorine sample had it's got hundreds and billions of atoms, right? Lots of atoms. Some of them, let's rub this carbon for a second. Some of them would be 37, some of them would be 35, right? You ionize them and you pass them through the magnetic field, you get a lesser deflection, you get more deflection depending on the mass of the particles, right? So here's a detector that's detecting these particles, and you've got a detector that is detecting the particles over here. So what you get is like, the particles that are receiving at this end, there are fewer of them. Like if there's lesser chlorine 37, the detector over here is going to detect fewer 37 plus 1 ions. And if the beam or the sample has a lot of chlorine 35, then the amount of charged particles that you're going to detect at this point would be a lot more. Hani, is this point clear?
So if the atom is lighter, it's going to produce more light ions.
No, it's not. Remember, you got chlorine 35 and you've got chlorine 37. Just let me put it this way. Now you've got a sample that's a mixture of both, right? Now in that sample, you'll have both of them, right? Now the sample could have a lot of chlorine 35s. So there could be a lot more chlorine 35 ions and very few chlorine 37. Remember, you have a random sample, and the sample has different chlorine atoms with different masses. Hani, is this point clear?
Yeah.
Now the point is, when all these ions, they turn into a beam and they start, like you turn them into a beam, and these particles are now flowing towards the magnetic field, right? So all these bunch of ions, they're flowing. Now clearly you can see in the sample you've got fewer chlorine 37s, right? So the amount of ions of chlorine 37 that you're going to detect are fewer, because in the original sample they're fewer. Hania, is this point clear?
Oh, yeah. Thank you.
Acha, so it depends. Yes.
सर ऐसे हो सकता है कि जहाँ से हमने मतलब क्लोरीन कलेक्ट किए हो वहाँ पर 35 की क्वांटिटी थोड़ी ज़्यादा हो जाए, मतलब वो 3 रेशो से भी ज़्यादा हो जाए, ऐसे तो नहीं होता ना?
नहीं, ऐसे हो सकता है,
मतलब वो
क्यों नहीं हो
एवरेज
सकता?
लगाया है।
नहीं, ऐसे बिल्कुल हो सकता है, because मतलब पूरी दुनिया में there's lots of chlorine samples, right?
Yes, यही
So
मैं
there might be, maybe there's a chlorine sample somewhere which is where there's a lot more chlorine 37. ठीक है? But the thing is that planet Earth, like what happens?
एवरेज है।
Acha, what happens on planet Earth is that over time, because Earth has been there for billions of years, over time, what happens is that the atoms, they kind of get distributed well, like on the entire surface, the atoms are well distributed. It's not that, if you had like I'll give you an idea. Let's assume the planet was formed, right? And there was this hill at one point where you had just chlorine 37, and there was this other place somewhere where you just had chlorine 35, right? Like over time, kya hoga? All the atoms would kind of, over time, billions of years, all the atoms would kind of get mixed up, right? So wo jo average hogi na, that
मतलब sort of
it would kind of be constant, theek hai?
Okay, sir.
But
Thanks.
but obviously they might be like, I mean, there would be some difference. Like if you take a chlorine sample in Pakistan and you take one chlorine sample in Australia, there might be some difference in the ratio of the number of chlorine 37s and the ratio of the number of chlorine 35s. But anyways, the mass, but the ratio would not be that different. Like if it's 3:1, to kahin aur na kisi aur jagah, it might be 3.1:1. So it won't be that huge a difference. So the point is, what the mass spectroscopy does is it gives you two informations. It gives you how many isotopes you got. At the same time, it gives you the relative abundance as well. So this is how you might get a diagram of this, or you might get questions. Where's the mass spectroscopy question? Just a second. Mass spectroscopy, just a second. Yeah. Or you might get a table. So they might, I'll just post this table. No, not this one. Let's take the easy one first. So this one is good. So let's take this example. Okay, so let's say they give you a graph. So this one, I think I forgot what the. So this one. Now this one is what it's I don't know what the atom was. Just a second, let me go back. The atom was, he just called it element X. So there was an atom, and he's asking you to calculate the relative atomic mass of this atom. So there's this atom which we're going to call X. It's got these isotopes. It has an isotope which has a mass of 74. It's got an isotope which has a mass of 76. You got a mass of 77 as well, 78 as well, 80 as well, and you got 82 as well. And the percentage abundance is given. So he gave the percentage, like 0.89% of the sample is this one. 9.37% of the sample is 76, has a mass of 76. So the percentage of each of the isotopes is given in the sample. So you know the relative percentage of each one of them. Now he's asking you to find the average. He's asking you to find the AR. Remember, by definition, what is AR? AR is the average mass of the atom. So the mass of the atom is 74, 76, 77, 78, 80, and 82. So I need to calculate the average of all the isotopes, just like we did for chlorine. Like chlorine was 35 and 37. This one.
Let's say 78, 80, 82 ये M1, M2 नहीं है?
कौन से?
So ये 78, 80 और 82 M1, M2 और जो हमारा होता है M.
नहीं.
सर जैसे हम निकालते नहीं है मास स्पेक्ट्रोमेट्री में, जैसे क्लोरीन के जो आइसोटोपिक कलर निकालते हैं मॉलिक्यूल,
वो तो A2 है. वो तो अभी तो वो करना ही नहीं है.
ठीक है सर.
ठीक है.
ओके सर.
ये सारे M है. Basically they're all M. मतलब this is M, this is M+2, this is M+3, M+4, M+6, and I think M+8. ठीक है. M का मतलब मॉलिक्यूलर आयन होता है, लेकिन उसका इससे कोई ताल्लुक नहीं है. ठीक है. तो A2 के अंदर करना है, उसको तो भी छोड़ दो. अच्छा, but this one, let's talk about the relative atomic mass. How do you calculate that? You calculate the average. Now the thing is, I'll just give you a short idea of how to calculate average first. जब भी आपने average निकालनी होती है, there are two ways of calculating the average. ठीक है. For example, I want to figure out the average of two numbers. बल्कि let me give you, अच्छा, these are the numbers 2, 2 और फिर 3 and 3. मुझे तो how do you calculate average? You add up all of them. ठीक है, that's what you do. You add up all of them And then what you do is you divide that by 4, right? Is this clear? That's how you calculate average, right? Is that all clear? So, well, what do you get for this? Anyone, what's the value that you're going to get for this? You clear? Amna, Mahad, Hania. Ahmed, is this clear?
2.5.
Achha, 2.5 aa rahi hai. So I think everyone knows how to calculate the average, right? So that's the way. You add up all of them and you divide by the total. But there's a problem here, and that problem is that this is a terrible way of calculating average, because what if आपके numbers बहुत ज़्यादा होते हैं? What if you had इस तरह का काम होता है कि you would have you'll have lots and lots of 2s and followed by lots and lots of 3s, right? And I ask you to calculate the average for this. Time ज़्यादा लगेगा. You'll be wasting a lot of time. 2 plus 2 plus 2 plus 2. I mean, you'll add up all of them and then you divide by the whole. I mean, so you're just kind of wasting time. And it's going to become an exercise in wasting time if the numbers keep on increasing. Like if you have 10,000 numbers and somebody is going to ask you to calculate the average, like if there's a bucket and it has 10,000 numbers in it and somebody asks you to calculate average for that, you're just wasting your time. I mean, how would you add up 10,000 numbers and then divide by 10,000? Okay, so that's going to be a waste of time. So there's another way of calculating average, and that is figure out the relative percentage. Okay, let's apply it to this. Figure out the relative percentage. Okay, you had this sample, right? But how much percent is 2? Like half of it is 2, right? So that means you do number 2, and that's 50% of the time in the sample you get 2, right?
Okay.
And the other 50% you're getting 3. Is this point clear? So what you do is this is another way of calculating average, and this is a much quicker way. So what you do is you don't start adding them up. You just figure out, okay, yes, this sample has 50% of the numbers in the sample are 2 and 50% of the number in the sample are 3. All you have to do now is, this is going to be your new way of calculating average. The average value, instead of the old method, this is the new one. Start summing them up. Multiply it by the percentage by the value. Okay, this is, you just start summing this up. So 50% multiplied by the value, what is the value? That's 2. And it has to be the fractional percentage. So it's going to be percentage divided by 100. Let me add that. So it's going to be 50% into 2 plus, what is the other one? 50% into 3. Or isko zara calculator pe calculate karo, it's going to be half into 2 plus half into 3. So it's going to come out to be what? Half into 2 is 1. Plus half into 3 is 1.5. And the answer comes out to be equal to, it's going to come out to be equal to 2.5. Now for small numbers, for a small set of numbers, it doesn't really matter. I mean, you can do this. But the real advantage of this is when you've got a big sample of numbers. Okay, for example, if you had a big set of numbers, like you had a box and it had all these numbers. It had lots of 2s, lots of them. And it had lots of 3s, lots of them. So calculating average the old way was difficult. It's going to be difficult. What you're going to do is, आप ये figure out करोगे भाई इस पूरे sample में कितने percent, how many times does 2 come in? So let's say somebody did that and they figured out that 80% of the numbers are are coming out to be 2. And the rest of the 20% are coming out to be 3. So if you know the percentage of each of the value, like kitni dafa, how many times you're getting 2, 80% of the times, how many times are you getting 3, that's 20% of the time. So instead of adding them all of them up, which would be very difficult to do, you can simply do that. It's going to be 80% over 100 times 2 plus the percentage of the other one, 20% over 100 times 3. And that will give you the average of the numbers. So is this clear? Or iska kya aa raha hai answer? What are you getting for this?
2.2.
Okay, so you're getting 2 point. You're getting 2.2. So just remember this new method of measuring average. When you want to measure the average, instead of actually adding them up and deal in percentages. In your sample, what is the percentage of this value? That's 50% of the times you're getting this. What is the percentage of this value? 50% of the time you're getting this. So all you have to do is multiply the fractional percentage by the value. And that's exactly how you're going to measure the average mass of the atom as well. Because remember, you know the percentage multiplied by the value, plus percentage multiplied by the value, plus percentage multiplied by the value. Keep on doing that and start summing them up. You'll find the average mass of the atom. Is this clear? Any questions?
Yes, sir.
So we'll continue with this. I mean, we'll do questions on this. We'll continue. We'll leave it here at the moment. We'll continue. We'll pick up things here tomorrow, and we'll try and do questions on this. So we'll try to measure the average of this. What is the average mass of the atom, of this particular atom, whatever it is? Okay. Okay, everyone. Take care.
Okay, sir. Allah Hafiz.
Allah Hafiz.